You'll recall that when we first started to take derivatives in Chapter 3, we took derivatives of functions that were very straightforward functions of x. So functions that we could write as y equals some function of x. And then later we learned how to take derivatives in cases where y couldn't be solved for a function of x. And we used what was called implicit differentiation. So far, second semester, we've been taking antiderivatives of functions that have just been plain functions of x. But recall that we do know how to take derivatives that contain both x and y. So our next step here in 6.4 is to use what's called separation of variables to find antiderivatives of functions that are written as functions of both x and y. So here, a definition for a separable differential equation, which is like the second friendliest kind of differential equation and the most difficult that we'll solve in this course. So it's a differential equation where dy dx is equal to some function of x multiplied by some function of y. Notice those two functions, f of y and g of x, they can't be added together, they can't be subtracted together, they have to be multiplied together. So if that happens, we can do what's called separate the variables. And we're going to move all the y's and the dy to one side. We're going to move all the x's and the dx to the other side. And then we're going to be able to find an antiderivative by integrating both sides. So check out this first example. So here's how I want to start if I'm going to solve this separable differential equation. Notice I have dy dx is equal to x squared times y squared. So I do have dy dx on one side, and on the other side I have a function of x multiplied by a function of y. My goal is to use algebra to get everything with an x on the right side and everything with a y on the left-hand side. So I'm going to multiply both sides by dx to get my next. So you can see what I have there. Now I'm going to try to get all the y's over to the left. Well, on the right-hand side, that y squared term, that y squared factor, it's multiplying. So I'm going to divide both sides by y squared. To get my new equation, which is dy over y squared equals x squared times dx. Notice now my variables are separated. If you got this far on the AP test, you would receive 1 point for having successfully separated the variables. Important to check after you've separated the variables, there should be no y's on the right-hand side, there should be no x's on the left-hand side, and your dx and your dy both have to be in the numerator. So you can't have the dx or the dy as the denominator in a fraction. Okay, so now my next step, if I want to find a solution for y, notice I have something that looks like the inside of an integral on both sides. That's actually my next step, is to take the antiderivative of both sides, which I'm going to indicate by putting an integral on both sides. So I'm going to integrate both sides. Notice that that next line that I've shown, it's just the equation right above it, but with an integral sign slapped on both sides. My next step is to actually perform that integration. So on the right-hand side, that's not so bad. The antiderivative of x squared is x to the third over 3 plus a constant. Over on the right-hand side, I have to think of that as dy over y to the negative, dy times y to the negative 2. I'm going to find an antiderivative by increasing the exponent by 1 and dividing by the new exponent. So I'm going to have y to the negative 1 divided by negative 1. And then I have this funny little thing, which is I need a plus c on the left, I need a plus c on the right. They're not necessarily the same thing, so I don't want to call them the same thing. So I just called the one on the left c1, called the one on the right c2. And just notice that if c is just some constant, then I could subtract c1 from both sides. On the right-hand side, I get c2 minus c1, which is just two constants subtracted together, which is just some other constant. So I won't expect you to go through that process of writing a c1 and a c2 again. You can just put one big plus c, and it only needs to go on one side of your equation. You can see here's my result. At this point I have two things left to do. I have to figure out the value of c. I can't leave c in my final answer. And my second thing I have to do, I'm supposed to report the function y, which means that I'm going to have to do whatever algebra it takes to isolate the y in this equation. So the order that you do these two things doesn't matter. I happen to find that most of the time it's easier to find c first and then worry about isolating y. So I'm going to go about finding c first. I recall that I said that y was going to equal 1 when x equaled 1. That's the initial value from my initial value problem at the beginning. So I'm going to plug those in. I'm going to have negative 1 over 1 equals 1 cubed over 3 plus a constant. So negative 1 equals 1/3 plus c. To isolate c, I'm going to subtract 1/3 from both sides, so I'm going to have negative 4/3 equals c. I'm going to go back to this top equation that I had, and I'm going to replace c with negative 4/3. So here I have negative 1 over y equals x cubed over 3. Instead of plus c, I'm going to write minus 4/3. And then last step, I'm going to take that equation, which at least has no c in it anymore. I'm going to try to isolate the y. So I find that the fastest way in this situation, my problem here is I have y in the denominator. I'm going to have to figure out how to get it out of the denominator. My recommendation here is to multiply through first by negative 1. So that's going to become 1 over y equals negative x cubed over 3 plus 4/3. If you wanted to, you might notice that right away I can write that right-hand side as one single fraction. So that could be 4 minus x cubed over 3, or negative x cubed plus 4 over 3. One step left. I'm trying to isolate y. Notice on the left side I have the reciprocal of y. It is legal to flip both sides of this equation as long as the right-hand side is written as one single fraction. And notice it here, it is here. So instead of 1 over y, I'm going to write y equals, and I'm going to flip the other fraction, 3 over 4 minus x cubed. Well, that's my final answer. Y is equal to 3 over 4 minus x cubed. When you're taking the AP test, my recommendation, my very sincere recommendation, is that at this point you stop, find that initial condition, y equals 1 when x equals 1, plug it in and make sure it still works. Because if it doesn't, something went wrong and you still have time to fix it probably. So 1 equals 3 over 4 minus 1 cubed. 1 equals 3 over 4 minus 1. 1 equals 3 over 3. That checks out. This is my answer. Notice y is isolated and I have no c. I actually have one thing left to do, which is to specify the domain for which this is the solution to our differential equation. So very few people have a picture of this function just cataloged in their head, but I hope you will notice that whatever this function looks like, it's going to have a vertical asymptote when the denominator equals 0. So it's going to have a vertical asymptote when 4 minus x cubed equals 0, and that's going to happen when 4 equals x cubed, or when x equals the cube root of 4. So the question is, this function, that's the only x value that's going to give us any problem. So this function has two pieces. It has one branch or one part that's going to go from negative infinity to the cube root of 4. And it's going to have another that goes from cube root of 4 to infinity. And our solution is going to be good on one piece or the other. The way we choose which piece is we look at that initial condition we had, which was our function must contain 1 comma 1. So with an x value of 1, is that in the domain negative infinity to cube root of 4 or cube root of 4 to infinity? Well, cube root of 4 is more than 1, so this x value falls into that piece of the domain. So this is what I would write. I would say y equals 3 over 4 minus x cubed. And I would specify x is less than the cube root of 4. Or I could say something like negative infinity is less than x, which is less than the cube root of 4. That's my final answer.